are going to spend some time in Chapter 5 today. So, in your old notes, the Chapter 4 notes, actually to round out the pages, we actually started Chapter 5 there. And the first thing at the bottom of page 56 of your old notes is a listing of some really important identities, many of which you already know. So you already know the reciprocal identities. You already know that cosecant is 1 over sine. No big deal there. Now, the quotient identities you may not be as familiar with, but they should make sense to you because it says the tangent is sine over cosine. Now, if you stop and think about your circular definitions, tangent is y over x, sine is y over r, and cosine is x over r. So if you put y over x over r, you see what happens? That becomes y over x. So to get your tangent value, you can always put your sine over your cosine. It's kind of a biggie. And then, of course, the reciprocal is true. The cotangent is cosine over sine. The Pythagorean identities are huge. And again, it should make perfectly good sense to you if we draw our little right triangle in standard position. This is theta, this is x and y and r. X-axis, vertical is y, radius of the circle. It is absolutely true that x squared plus y squared equals r squared. And we can take that equation if we want and divide everything by r squared, creating a new equation, which would be x over r squared plus y over r squared equal to 1. But we know that x over r is cosine, so this is cosine squared, this is sine squared, and so it is true that always, this is a biggie, put a star by it, cosine squared plus sine squared is 1. Now notice when I wrote that, I wrote cosine squared like this. And that's the way that we will write it. That's the way everybody writes it. It's too cumbersome to put in the parentheses. And if you don't put in the parentheses, then you can see all kinds of confusion that could happen. This looks like the cosine of theta squared, which isn't what we mean at all, but that's what it looks like. So when you have powers on your trig functions, the power goes before the angle. So if I have the tangent of 30 and I want to square that, I'm going to put it right there. That tells me I'm squaring the tangent of 30. Just a notational thing. All right, then we have the cofunction identities. And I'm not sure if you have, really thought about this. I mean, I know when we first started this, I just sort of slapped up. I mean, we had the big three, sine, cosine, and tangent. But then I just kind of slapped up the other ones and said, okay, these are the reciprocals. And you looked at those names, and I don't know if you tried to make any sense out of those names or not. So let me try to explain what it means to be a cofunction. And cofunctions are the co's in your names. So sine and cosine are cofunctions. Sine, cosine, cofunction. Tan and cotan are cofunctions. And secant and cosecant are cofunctions. Now, cofunctions is different than reciprocals. This pair is both. They're cofunctions and reciprocals. But these are not. This pair is not reciprocals. But they are cofunctions. And here's what that means. Let's go back to our triangle. And let's just say this is a 40-degree angle. Then wouldn't this automatically be 50? Yes. because these two are complementary. Oh, I think I spelled that wrong. Okay, complementary. First two letters of complementary, co-functions. So what happens, okay, let me just label my sides. This is X and Y and R, okay? So if or maybe I should use different letters because that's going to get confusing. So I'll say A, B, and C, okay? So I want you to tell me what the sine of 40 is. The sine of 40 would be opposite over hypotenuse, so B over C. Now, what about the cosine of 50? Well, there's 50. The cosine of 50 is adjacent over hypotenuse. Notice that the sine of 40 is the same as the cosine of 50. And if you don't believe me, type it in on your calculator. Make sure you're in degrees. Cosine 50 is the same as sine 40 because the co-functions have the same value for complementary angles. So the tangent of 80 is equal to the cotangent of 10. That's what it means to be co-functions. Okay, so that's written formally, pi over 2, remember, is 90. So the sine of 90 minus theta, that would be the sine of the complement, is equal to the cosine of the original angle. Okay? So that's what it means to be co-function identities. The odds and the evens we've already talked about. When we have even functions, so the cosine is an even function, and what that means is if you input a negative, it disappears. Cosine is even. So anytime you have a negative, you're taking the cosine of a negative, you're allowed to drop the negative. This is even. The only other function on there that's even, you can look at it and see, the only other function that's even is the secant. All of the rest of the functions are odd. And odd means if you put in a negative, you're going to get out a negative. So if you have a problem and it's written like this, you can translate it into this. And I said the other day, I like to do that when I'm graphing because I find this reflection a whole lot easier than this reflection. That's my personal issue. Okay? So these are the odd evens. The odd evens tell you how to deal with internal negatives. Mrs. Ford, am I supposed to know all that? Yep, you are. The good news is, like I said, if you stop and think about it, you already know a lot of it. I just tried to explain a little bit here, make some connections for you. The co-functions are the complementary issues where the secant of 20 is equal to the cosecant of 70. That's what it means to be co-function. Odd even, we already kind of know. This one is huge. Make sure you know it. I did not derive the other ones for you. I will real quick because there are 3 Pythagorean identities that you want to know, but they all come from this one. So you memorize, absolutely, you memorize this. That is memorized. If you take this equation, sine squared plus cosine squared is 1, and you divide it by cosine squared, you get 1 plus, okay, now this is sine over cosine. We just talked about that, or maybe I didn't write it down, or whatever. Sine over cosine is tangent. So this is really tangent squared. And this, of course, is secant squared. So that's another one of your Pythagorean identities. So a Pythagorean identity, first of all, they're all squared, Pythagorean theorem, and you have one that links sine and cosine. You have one that links tan and secant. And then if we go back to the original identity, sine squared plus cosine squared is 1. And this time we divide it all by sine squared. Look at the other Pythagorean identity, which is 1 plus cotangent squared equals cosecant squared. So there are only 3 Pythagorean identities, and they each link 2 functions. All right, those identities, all those identities are important, so please start working on those. It's okay if you wait until after your test to start working on those, but you do need to start working on those. All right. Now we're going to do some problems. So the first problem we're going to do, I'm in my notes now, problem number 1. And this actually is a review problem. This you should know how to do without any identities at all. Now you can use identities to help you if you want, but I don't think you need it. All right, let's look at what it says. It says the tangent is 5 over 1, and the cosine is positive. And then we got to find a couple other things, but I need to draw a picture of this first. This could be a test question. The tangent is positive, and so is the cosine. Now, keeping in mind that tangent is sine over cosine, or y over x, and cosine is x. If sine over cosine is positive, and cosine is positive, then doesn't sine have to be positive too? Also? So we need a quadrant that has a positive sine and a positive cosine. Well, that only happens one place. That happens in quadrant 1. Now, I see a point of confusion, potential. I'm going to draw a picture of the angle whose tangent is 1, and this would be root 26. So the sine is 5 over root 26, or 5 root 26 over 26. And the cosine is 1 over root 26, or root 26 over 26. It is absolutely 100% true that tangent is sine over cosine. But when you have a tangent given to you, that does not mean that the sine is 5 and the cosine is 1. It means the ratio of the sine to the cosine is 5 to 1. What you can automatically do is say, okay, that's y over x. So you can say that, but you cannot say that the numerator is the sine value and the denominator is the cosine value. Okay, I hope that makes sense to you. When we say sine over cosine, that's a ratio. That's a ratio. So if that's 5, then that means the top number is 5 times the bottom number. It doesn't mean that the sine is 5 and the cosine's 1. Sine can't be 5, right? You know that. All right, number 2 says the cosine is 0.34, and we have to find the sine of theta minus pi over 2. Okay, well, first of all, there should be some alarm buttons going off, because we have identities that sort of look like this, but what's the difference? The identities that we have, this could kind of be our Bible for a while. those identities that we have, this is backwards, right? It's pi over 2 minus theta. So I'm going to go ahead and change that and make it the opposite of pi over 2 minus theta. So in other words, I'm factoring out a negative 1 so that I can turn this around and it looks like what it's supposed to look like on my identities. Look at the cofunction identities. It's pi over 2 minus theta, not theta minus pi over 2, and these are different. Okay, so I factored out the negative 1. Now I have the sign of a negative. So that negative can come out in front. So I am trying to figure out the opposite negative, the opposite of the sign of pi over 2 minus theta. Well, don't my cofunction identities tell me that the sign of pi over 2 minus theta is the cosine? So I know that the sign of pi over 2 minus theta is 0.34, because they told me the cosine was 0.34. That's fact. But in this problem, I don't want the positive sign, I want the negative sign. So the answer to the problem is negative 0.34. Negative 0.34. So I used a couple of my identities there. I had to rewrite this so it matched my identities. Then I had a negative buried in there that I pulled out in front. So I had the opposite of the cosine, so 0.34. All right. Now, going to my new notes now, page 57. And we're going to simplify. Now, keep your old notes handy because that's where your identities are. And if you don't want to keep the whole packet, because it's kind of bulky, rip off that last page and staple it onto here or something so that you've got those identities handy until you get them figured out. All right, so we're going to simplify this. Now, you know, it looks terribly scary, but I do not want you to be scared, okay? It looks scary, but it really doesn't have to be at all. Think about a normal, like, math expression that had all these powers in it. Would a possibility be, you can't add those, they're not like terms, but would a possibility be to factor it? We can take a sign, one sign, out of sine cubed, and that would leave us with sine squared. And we can take a sign out of this, and that's going to leave us with, oh my gosh, ding, 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 ding. Look at your identity sheet. The fundamental trigonometric identity, the big one, is right here. We love that identity because what's sine squared plus cosine squared? 1. So you have basically just sine times 1, which is sine. So the directions were take this big complicated thing and simplify it. Boom! All you did was a simple factoring, and this popped up. So you took it out and replaced it with 1. Wow, that is incredible. All right, let's see if the next one works out as nicely. Simplify. Now again, you're just starting this, but some things should be sort of like just natural to you. Nothing cancels. Nothing factors. In fact, it's kind of already been factored. So I don't see anything like profound there. So what if I multiplied the top together? What if I FOILed? Right from the beginning, I want you guys to understand something. All these problems are going to look different. And there isn't a single thing that's right. You just have to do something. So when I look at that problem, and I don't see any canceling or any identities popping out at me, I'm going to go ahead and multiply those together and see what happens. So when I FOIL these, I get secant squared, and remember we write it like this, secant squared, and then the outsides and insides are going to cancel, so that's my numerator. Secant squared minus 1. Now I know what you're thinking. You're thinking, that's all well and good, Mrs. Ford, but I don't really see anything happening here. Well, that's because you're just getting started. I want you to look at this numerator. The numerator has a 1 and a secant squared in it. You have a Pythagorean identity that has a 1 and a secant squared in it. Remember, the identity as written is 1 plus tangent squared is secant squared. But that's an equation, that's an identity, it's true all the time. So what if I move this 1 over here? Then wouldn't it say tangent squared equals secant squared minus 1? So see that numerator right there? That numerator is really tangent squared. Because of this identity. So what we're taking away from this right now is that sometimes our identities show up in different forms. So it isn't always going to say 1 plus tangent squared. Sometimes it'll say secant squared minus 1, but it's the same identity. Okay, so I changed that, so now I've got tangent squared over sine squared. Well, now wait a minute. That's tangent squared divided by sine squared. But tangent squared is sine squared over cosine squared. So I have sine squared over cosine squared divided by sine squared, which is the same as multiplied by 1 over sine squared. Don't you love it when it all comes together? These cancel, and we're left with 1 over cosine squared, which is secant squared. So that mess simplifies down to secant squared. Now, I wish I had time to do this problem a couple of different ways, because all of these problems can be done a multitude of ways. I don't. This is it. This is how I did it. But if you have a different thought, especially as you get better at this, you'll be able to come up with some really cool and creative ways. And I can't wait to see them. But given the time I have, I'm just going to do each problem once. All right, here we go. Next, simplify again. We're going to simplify again. This time we have cosine over 1 minus sine over cosine. Now, I would agree that this is tangent. And if you want to change it to tangent, that's up to you. I would not. Because this is sines and cosines. These are two fractions. I'm going to need a common denominator. I really would prefer not to have cosine, sines, and tangents in the same problem. It's just too much. But you can do it, and it'll work out. I'm explaining my logic. Also, we have an identity that says sine squared plus cosine squared is 1. So it is absolutely true that cosine squared equals 1 minus sine squared. That is absolutely true, and you'll use it a lot. It's just the fundamental identity with things moved around. But notice, these are squared. This is nothing. You cannot change 1 minus sine. You can change 1 minus sine squared into cosine squared, but you can't change 1 minus sine. Okay? So, I kind of gave it away a minute ago. I'm looking at this problem. Lots of things are going through my head. But bottom line is I've got two fractions, so I'm going to add them together. And to add them together, I'm going to get a common denominator. So, this fraction needs to be multiplied by cosine over cosine. And this fraction needs to be multiplied by 1 minus sine over 1 minus sine. Remember, when you get a common denominator, you make the denominators match. But whatever you multiply the bottom by, you have to also multiply the top by. So this is cosine squared over cosine times 1 minus sine. This is, okay, now I gotta be careful here. I'm gonna go ahead and, this is sine minus sine squared over cosine 1 minus sine. You really have to watch out for the SIGNs. So I left my negative there, my subtraction there, and I just distributed here. Now the denominators are the same, so I can go ahead and make one fraction and put all the numerators up there. So it's going to be cosine squared minus sine plus sine squared, because I'm subtracting this whole quantity, so minus sine plus sine squared. Well, I know we just started, today's day 1, but I'm hoping that your heart is like beating a little bit faster now, because what do we have right here? Cosine squared plus sine squared. We have a 1. So we have 1 minus sine on top. These two make a 1. And on the bottom, we have cosine times 1 minus sine. How cool is that? So we have 1 over cosine or secant. So the direction said, simplify this big, huge, hideous mess. And I just did. Okay. Now the directions have changed, and now we are solving. All right, so how does that change things? Well, let's see. Cosine cubed over sine equals cotangent x. And I'm solving between 0 and 2 pi, which means I'm in radians, and I'm looking all the way around. So my answers are eligible in every quadrant, 0 to 2 pi. Okay, so this is an equation. It says solve this equation. So I'm going to go ahead and multiply the sign over to here. So I have cosine cubed equal to cotangent times sine. Now wait a minute, what do we know about cotangent? Cotangent is cosine over sine. So what do I really have over here? I'm going to multiply this sine over here. And what do I really have over here? Don't I just have cosine? So cosine cubed equals cosine. Now, you're tempted, I'm 100% positive, that you are tempted to divide by cosine. Guys, you cannot divide by a variable. Do not divide. This is going to come up over and over and over again. It's going to tempt you every time, and you're going to be wrong every time you do it. So do not divide if a variable is involved, because it could be 0. Cosine can be 0, and we don't want to divide by 0. So what we're going to do instead is we're going to subtract it. Because if I subtract it over, now I can factor it out. And since my equation is set equal to 0, I can actually set each of these equal to 0. Just like I do in a regular Algebra 1 equation. I factor, set each factor equal to 0. So either the cosine is 0, I'm going to figure out where that happens, or the cosine is plus or minus 1. Take the square root of both sides, plus or minus. Now remember, when you get numbers like zeros and ones, we're going to look at our unit circle. There's our unit circle. Radius is 1. Quadrantal angles. So right one, up one, left one, down one. Keeping in mind that cosine is x on the unit circle, x over r, but r is 1. So cosine is x on the unit circle. Where is the cosine 0? Where is the cosine 0? Looks like pi over 2 and 3 pi over 2. $90 and $270. Okay, and then where is the cosine 1 or negative 1? Well, the cosine is 1 here, x over r, 1. So that would be 0. I'm going to add it over here. That would be 0. And over here it's negative 1, so that would be pi. And that's all the way, I was going all the way around. Yep, all the way around the circle. Notice that the way the directions are written, it's like this. So while 0 and 2 pi are the same angle, basically, 2 pi is not included, that's an open interval, so we only write 0. Now, we're not done, because we can't include, remember, this is the equation that we're solving, right? That was the original. And we cannot include these two answers. I wish you were here so I could hear your thoughts on that. We can't include those two answers because the cotangent of 0, think about what your cotangent looks like. The cotangent of 0 and the cotangent of pi are undefined. And you can't include values that make your function undefined. So there you go. The only answers to the problem are 90 and 270. In other words, pi over 2 and 3 pi over 2. Whew, that's fun. Let's do one more. I think we have time to do one more. And then we'll call it a day. Yep. All right, so here we go. Another solve, find all solutions So this one does not give me a defined range or domain. It just says anything. Which, coming back to what I just said about this one, would mean if we were giving all answers and we had included 0, then we would also include 2 pi, 4 pi, and so on. So all answers means we're looking at the coterminals also. But before we do that, we'll worry about that at the end. Let's get this thing solved. I'm hopeful when you look at it that you see a quadratic equation and squared. And a quadratic equation needs to be set equal to 0 and solved. Hopefully by factoring. If they don't factor, this one does, so we're all good. But if it doesn't factor, you can use the quadratic formula. A, B, C, and instead of solving for x, you're solving for sine x. But this one factors. So we have 2 sine and sine, because when I multiply these two together, I get my 2 sine squared. I need a 1 and a 1, and I need one of them to be negative. I think it's going to be this one. Because when I FOIL these together, the outside terms would give me a positive 2 sine, and the inside terms give me a negative sine. So that's how I end up with that. All right, so set these equal to 0 and solve. So this one says the sine equals 1/2, and this one says the sine equals -1. I'll do this one first because I have my handy dandy unit circle here. And ones, remember, there's no triangle that has opposite over hypotenuse matching. You got to use the circle. Where is the sign -1? Sine is associated with y, and where is y -1 in the unit circle? Right here. So this answer is 3 pi over 2. In radians, if I were in degrees, I'd say 270. That's the only place on the unit circle, or anywhere, it's the only place the sign is -1, is right there. Now, where is the sign 1/2? Well, this is a good test review, because you need to know this for your test. The sign is positive here and here, and if the sign is 1/2, isn't that a 30-degree angle? In radians, a 1/6 of pi, pi over 6. So one angle is pi over 6. And the other one would be this one, which is pi minus pi over 6, or 5 pi over 6. Pi minus pi over 6. 150. 180 minus 30. All right, so those are the answers if I'd had these directions. I'd be done if I had those directions. But it says find all of them. So think about that. It's not just pi over 6. Isn't it all the way around and back up to pi over 6? It's all of the coterminal angles. So pi over 6 plus or minus 2 pi n, 5 pi over 6 plus or minus 2 pi n, 3 pi over 2 plus or minus 2 pi n, and n is a whole number. When you add or subtract 2 pi n, what you are doing is adding or subtracting revolutions. No revolutions, 1 revolution, 2 revolutions, 3, 4, 5, 6, however many revolutions you want to add. Some whole number of revolutions, 1, 2, 3, 4, 5, 0, 17, to the original answers. And you're adding and subtracting. So you're not only getting the positive coterminal angles, but you're also getting the negative coterminal angles. Okay, Mrs. Ford, in the last problem, you made me exclude some of my answers because some of those answers made the cotangent undefined. You do not need to worry about that in this problem, kids, because this problem only involves sine. And is the sine ever undefined? Think about its graph. Does the sine have asymptotes? No. The sine is never undefined. So any answers you get are going to be good to go. Same is true of the cosine. But if you have an equation that involves any other function, tangent, secant, cosecant, cotangent, you got to make sure that whatever you come up with as an answer does not make it undefined. All right, so we'll stop there. We got a couple more to go, it looks like next time. So we'll do that, and I'll see you later. Hope you're having a good day.